Have you ever looked at the stars and felt infinitely small? That feeling is not a weakness. It is a survival instinct. Somewhere deep in your brain, beneath layers of civilization and self-assurance, lives a primordial fear. The fear of darkness, of cold, of endings. The same fear that drove your ancestor to huddle close to a fire hundreds of thousands of years ago. Fire was his entire universe, his only grip on chaos, a small dancing flame against the infinite night. Now look at the sky in daylight. Up there burns a fire the size of 1,000,000 Earths. It has been burning for 4.5 billion years and does not notice us, does not know we exist, don't know we are afraid, do not know we dream. But we know about it, and in that is everything. That tiny asymmetric fact hides either our extinction or our immortality. Because a species that learned to comprehend a star will sooner or later ask itself one question: what if we could tame it? Look up at the sun, really look at it, not with your eyes, which would be blinded, but with your mind. What do you see? A yellow ball in the sky? A source of warmth for your skin? A clock that marks the day? To a physicist, the sun is none of these things. It is a terrifyingly inefficient, unshielded thermonuclear reactor, a ball of hydrogen fusing into helium at a rate that defies comprehension. Every single second, the sun converts 600 million tons of hydrogen into helium. Every single second, it releases an amount of energy equivalent to trillions of nuclear bombs. It screams energy into the void in all directions. And what do we do with this bounty? We, the inhabitants of the third rock from the star, catch only a tiny, pathetic fraction of it. The Earth intercepts merely 1/2 billionth of the sun's total output. The rest, more than 99.999999995%, streams past us, lost forever into the cold dark of deep space. It is the greatest waste in the solar system. We are a civilization of scavengers, huddled around a bonfire, burning fossilized plants and splitting heavy atoms, while a fusion engine of godlike power burns overhead, untapped and ignored. This realization is the starting point for one of the most audacious ideas in the history of science. The idea that a truly advanced civilization would not just live near a star, but would enclose it. They would build a shell around their sun to capture every single photon, every single joule of energy. They would turn the star into a battery. This is the concept of the Dyson Sphere, and it is the ultimate destiny of any species that survives long enough to grow up, to understand why we would ever need to do this, why we would need to disassemble planets to build a cage for a star. We have to look at the mathematics of growth. In 1964, a Soviet astrophysicist named Nikolai Kardashev looked at the history of human energy consumption and noticed a clear pattern. For thousands of years, our energy use has grown exponentially. We went from burning wood to burning coal and oil to splitting the atom. Every leap in civilization, the Industrial Revolution, the Information Age, was powered by a massive jump in energy consumption. Kardashev realized that if this trend continues, we will eventually run out of energy on Earth. We will strip the crust of uranium. We will cover every inch of the desert with solar panels, and it still will not be enough. Based on this logic, he proposed a scale to classify civilizations not by their philosophy or their art, but by their energy budget. It is a ladder of cosmic evolution. A Type 1 civilization, a planetary civilization, has mastered the energy of its home planet. It can harness all the sunlight that falls on its world, control the weather, mine the crust and the oceans, and utilize geothermal power perfectly. We are not there yet. We are currently about a type 0.73. We are still burning dead dinosaurs and arguing about the thermostat. A type 2 civilization, a stellar civilization, has outgrown its planet. Its energy needs are so vast that the only source sufficient to feed them is the star itself. This civilization builds a Dyson Sphere. It captures 100% of the star's output. It has access to roughly 10 billion times more energy than a Type 1 civilization. With this power, it can terraform other worlds, move the star itself, and become effectively immortal. A Type 3 civilization, a galactic civilization, has colonized the entire galaxy. It harnesses the energy of billions of stars. It plays with black holes. It operates on a scale that to us would look like magic or divinity. The gap between these types is not just quantitative, it is qualitative. A Type 2 civilization does not just have more energy, it can do things that are physically impossible for a Type 1. It can manipulate matter at the fundamental level. It can build computers the size of planets. It can transmit information across the galaxy. The transition from Type 1 to Type 2 is the most critical step in the life of a technological species. It is the moment when the species stops being a passive passenger on a planet and becomes the active pilot of a solar system. It is the move from inhabiting the world to engineering the world. But this transition is also a trap. The energy demands of a growing technological society are relentless. Any civilization that survives for a few thousand years after discovering industrial technology will inevitably run into an energy crisis. They will have to build a sphere, or they will stagnate and die. It is a Darwinian imperative: expand or expire. Imagine the sheer scale of the engineering required for a Type 2 transition. The Sun is 865,000 miles wide. To build a shell around it at the distance of Earth's orbit, 1 astronomical unit, you would need a surface area of approximately 280 quintillion square kilometers. That is 550 million times the surface area of the Earth. Where do you get the material? You have to disassemble planets. You have to take a world like Mercury or Venus, strip it down to its core, and reprocess every single atom into solar collectors and structural beams. This is planetary demolition on an industrial scale. To a Type 2 civilization, a dead rock like Mercury is simply a pile of raw materials waiting to be used. It is a quarry. The ethics of the cosmos change with the scale of the energy. This concept challenges our deep-seated planetary chauvinism. We tend to think that living on the surface of a ball of rock is the natural, optimal way for life to exist. But planets are inefficient. They have gravity wells that make it hard to leave. They have atmospheres that block light. They have tectonic activity that destroys cities. A Dyson swarm of orbiting habitats offers a much better deal. You can have trillions of habitats, each with perfect gravity, perfect weather, and unlimited sunlight. You can support a population of quintillions of humans or post-humans. The total living area inside a Dyson swarm would be millions of times greater than all the habitable planets in the galaxy combined. Why search for Earth 2.0 light-years away when you can build a million Earths right here, using the spare parts of the solar system? The sphere is not a cage. It is a mansion. It is the ultimate urbanization of space. The path to Type 2 is fraught with danger. Disassembling a planet requires machines that can self-replicate. It requires von Neumann probes, robots that can mine ore, build copies of themselves, and repeat the process exponentially. If you start with one robot on Mercury and it replicates once a month, within 30 months you would have 1 billion robots. Within a few decades, you could turn the entire planet into a cloud of mirrors. This exponential manufacturing is the key. We are not building the sphere with our hands. We are growing it like a bacterial culture made of steel and silicon. The Kardashev scale forces us to confront the exponential nature of technological time. The sun is 4.6 billion years old. It has another 5 billion years to go. Human civilization is maybe 10,000 years old. Industrial civilization is 200 years old. On the cosmic clock, we are a flicker. A Type 2 civilization could be millions of years old. Their technology would be indistinguishable from the laws of physics. When we look for them, we should not look for people like us, but slightly more advanced. We should look for entities that have reshaped their entire stellar environment. We should look for stars that are invisible because they are wrapped in shells. We should look for the infrared excess, the waste heat that must escape the sphere according to the laws of thermodynamics. A Dyson Sphere would not shine invisible light. It would glow in the infrared like a warm coal in the dark. We have scanned the sky with infrared telescopes. We have found millions of infrared sources. Dust clouds, young stars, dying stars, but we have not found a definitive Dyson Sphere. This silence is the Fermi paradox writ large. If the galaxy is old and Type 2 civilizations are inevitable, where are they? Why is the night sky not filled with the dull red glow of caged stars? Are we alone, or are we just looking for the wrong thing? The energy hunger of humanity is currently driving us toward ecological collapse. We are burning the furniture to heat the house, but the Kardashev perspective offers a way out. It suggests that our current crisis is a growing pain, a bottleneck we must squeeze through to reach the next level. Solar power is the gateway to Type 1. Fusion power is the gateway to Type 2. If we can survive the adolescence of our species, the era of fossil fuels and planetary wars, the universe opens up, the resources are there, the energy is there. The sun creates more energy in a single second than humanity has used in its entire history. It is just waiting for us to build the bucket to catch it. The transition to a stellar civilization is not just about building big structures. It is about a shift in consciousness. It is about realizing that the solar system is not a collection of sacred objects, but a toolkit. It is about accepting the responsibility of being the gardeners of a star. As we stand on the threshold of the space age, launching rockets that can land themselves and telescopes that can see the dawn of time, we are taking the first baby steps of Kardashev's ladder. We are the Type 0 ancestors of the star builders. And while the idea of dismantling Mercury seems like madness today, to our descendants it might be as obvious as cutting down a forest to build a city. The imperative of life is to expand. The imperative of intelligence is to control. And the ultimate control is to put a leash on the sun. A solid shell around the sun is physically impossible. The stresses would tear any known material apart, and the sphere would have no gravity to keep it centered. It would drift until it crashed into the surface. The practical solution is not a shell, but a swarm. A cloud of billions of independent satellites orbiting in dense formation, weaving a net of light and shadow around the sun. This Dyson swarm is the realistic architecture of a Type 2 civilization, a fluid, dynamic, living system that evolves over time. The first target on the demolition list is the iron planet Mercury, and the process that will turn it into a shimmering cloud of intelligent mirrors is known as the Great Dismantling. Imagine holding a marble in your hand. This marble represents the Earth. Now imagine you want to build a swarm of satellites around a basketball representing the sun, even though we are not building a solid shell, which we know is physically impossible. The sheer surface area we need to cover with collectors is mind-bending. The surface area of a sphere at 1 astronomical unit is about 550 million times the surface area of Earth. To build even a thin solar collector array covering this area, You would need more material than exists in all the asteroids, comets, and moons of the solar system combined. You need a planet, a whole one, and not just any planet. You need a planet rich in metals, close to the sun and devoid of an atmosphere or a biosphere. You need Mercury. Mercury is the perfect quarry. It is dense, about 70% iron by mass. It has no moon, almost no atmosphere, and low gravity. Only 38% of Earth's. This makes launching material from its surface incredibly cheap in terms of energy. And it sits deep in the sun's gravity well, so solar panels near Mercury receive nearly 7 times more energy per square meter than panels near Earth. The dismantling does not begin with pickaxes or shovels. It begins with the sun itself. You land an automated self-replicating factory on Mercury. It mines the regolith, extracts iron, aluminum, and silicon, and builds solar collectors. It deploys these collectors on the surface. They collect energy. The factory uses this energy to build more robots and more collectors. This is the exponential growth phase. Within a few decades, a significant portion of Mercury's surface is covered in solar panels. Then comes the launch loop, or mass driver, a giant electromagnetic railgun miles long. You load the processed material, compact packages of folded mirrors and electronics, into the railgun and fire them into space. Because Mercury has no atmosphere, there is no air resistance. You can shoot things directly into orbit. You create a continuous river of material leaving the planet. Once the first swarm of mirrors is in orbit around the sun, they do not just beam power back to Earth. They beam power back to Mercury. They fire lasers at the planet's surface. This concentrated energy vaporizes the rock, creating a plume of plasma. Magnetic fields trap this plasma, separate the elements, and feed them directly into the orbital factories. You stop digging. You start evaporating. The planet is peeled away, layer by layer, like an onion. The energy required to dismantle Mercury is immense, roughly 10 to the 30th joules, but the sun provides 10 to the 26 joules every second. Once the feedback loop is closed, the dismantling accelerates. Mercury could be consumed in as little as 40 years. The iron core becomes the structural beams of the swarm. The silicates become the mirrors. The oxygen is used for fuel or habitat atmospheres. A dead world dies so a living system can be born. The density of the swarm determines how much energy you catch. You start with a single Dyson ring around the equator of the star. This catches perhaps 1% of the light. Then you add more rings at different angles, creating a Dyson cage. Eventually the rings overlap so densely that they form a complete sphere. From the outside, the sun would slowly dim. First it would look like it had a belt. Then it would look fuzzy. Finally, as the swarm thickens, the visible light would vanish completely. The star would disappear. In its place would be a dark object radiating only the waste heat of the civilization inside, a glowing infrared ember. Navigating trillions of objects moving at orbital velocities in such a confined space is a nightmare. A single collision could trigger a Kessler syndrome cascade, grinding the entire swarm into dust. The control system would need to be a Type 2 intelligence in itself, an automated traffic control system processing exabytes of data per second. The mirrors are not passive. They are solar sails. By tilting them relative to the sun, the pressure of the photons can push them back into position without using propellant. The star itself holds the swarm up with its own light. There's also the concept of the statite swarm. A statite does not orbit. It hovers, using a massive solar sail to balance the pull of gravity exactly against the push of light pressure. It sits motionless over a specific spot on the star. A shell of statites would be truly stationary. This would require incredibly light, thin materials such as graphene or carbon nanotubes. The implications of living inside a swarm are profound. In a swarm of rotating habitats, you have perfect gravity. You have day and night cycles controlled by shutters. You have no weather disasters, no earthquakes, no volcanoes. It is a curated existence. The total habitable surface area of a Dyson swarm at 1 astronomical unit is roughly 600 million times the surface area of Earth. That is enough room for every human who has ever lived to have their own continent. The population bottleneck is broken forever. We could have a population of quadrillions, and the density would still be lower than in rural Wyoming. This abundance changes the nature of society. Scarcity, the driving force of human history, war, and economics, evaporates. Energy is free. Space is effectively infinite. Matter is recyclable. What becomes the new currency? Reputation, creativity, novelty. In a post-scarcity Type 2 civilization, the only thing that cannot be manufactured is originality. The dismantling of the planets raises an ethical question. Do rocks have rights? Is it moral to destroy the solar system to build a house? A Type 2 civilization might preserve certain worlds as nature reserves, encasing them in their own mini shells, or they might digitize the biology and recycle the water. To a mind that thinks on the scale of stars, a single bacteria might be data, not a sacred life form. Once the swarm is complete, the view from any preserved habitat would be strange. The sun would be gone. The sky would be black during the day, lit only by the other stars and the glittering points of the swarm itself. Streaks of communications lasers and the faint glow of waste heat. We would no longer be under the sun. We would be around the source. A planet is a single point of failure. An asteroid can wipe it out. A plague can sweep through it. But a swarm is decentralized. It is redundant. If one habitat fails, a million others survive. It is immune to natural disasters. It is hard to attack. A Dyson swarm is the ultimate survival bunker. It ensures that the species cannot be extinguished by anything less than the death of the star itself or a galaxy-wide cataclysm. In 2015, a team of citizen scientists noticed a star in the constellation Cygnus that was breaking all the rules. Its light curve looked exactly like a star being surrounded by a half-built construction project. The star was called KIC 8462852, better known as Tabby's star. For a brief, electrifying moment, the world wondered whether we had caught a Type 2 civilization in the act of the great dismantling. In the sterile, climate-controlled silence of the Kepler Space Telescope's data archives, among millions of predictable light curves, one signal stood out like a scream in a library. It was 2015. The Kepler mission had been staring at a patch of sky in the constellation Cygnus for 4 years, searching for the tiny rhythmic dips in brightness caused by planets passing in front of their stars. A planet like Earth blocks a fraction of 1% of a star's light. Jupiter might block 1%, but the star KIC 8462852, an ordinary F-type star slightly hotter than our Sun, was doing something impossible. Its brightness dropped by 15% at one point and by 22% at another. The pattern was chaotic. It dimmed for days, then weeks. It looked as if something massive, irregular, and constantly changing was orbiting it, something that was not a sphere, something that looked less like nature and more like engineering. When the astronomer Tyvetha Boyejun published the paper describing this anomaly, she titled it, "Where's the Flux?" a polite academic pun. The media gave it a different name, Tabby's star. For a brief, electrifying moment, the entire world looked up and wondered if we had finally found them. If we had caught a Type 2 civilization in the act of building a Dyson swarm. The excitement was rooted in the specific strangeness of the data. Natural objects tend to be symmetrical. Planets are round, stars are round, even dust clouds, over time, spread out into uniform disks. But the light curve of Tabby's star suggested something lumpy, with sharp edges blocking light in a way that solid rock should not. The dips were jagged, not smooth and U-shaped like a planetary transit. This led astronomer Jason Wright to say words no scientist says lightly. Aliens should always be the very last hypothesis you consider. But this looked exactly like something an alien civilization would build. A swarm of giant solar collectors orbiting the star. If a civilization were dismantling a planet to build a Dyson swarm, you would see precisely this. A chaotic cloud of massive flat panels, some finished, some under construction, drifting in front of the star and blocking huge amounts of light in an unpredictable rhythm. The scientific community scrambled for natural explanations. Was it a swarm of comets? A massive family of giant comets breaking apart could create a cloud of dust and debris. But the math was brutal. To block 22% of a star's light, you would need something like 648,000 giant comets all passing in front of the star at once. It felt contrived. Was it a planetary collision? That would create a massive debris field, but it would also produce a lot of infrared radiation from the friction. Telescopes looked for the heat and found nothing. The debris was cold. The mystery deepened in 2016 when old photographic plates from the 1890s showed that Tabby's star had been fading for over a century. Its total brightness had dropped by roughly 20% in 100 years. Stars like this are stable. They do not simply dim by 20% in a human lifetime. This secular dimming suggested that whatever was blocking the light was growing. The construction project hypothesis gained ground. If a civilization were exponentially increasing its collector area, the star would dim over decades. We were watching the lights go out, yet the alien megastructure idea faced a major hurdle: the lack of technosignatures. If aliens were building a Dyson swarm, they should be noisy. Using radio waves or powerful lasers, the SETI Institute listened. They heard silence. Other telescopes searched for laser pulses. Nothing. A civilization advanced enough to eat a planet might use communication technologies we cannot even imagine. Or perhaps the structures were automated and silent. In May 2017, the star dipped again. Telescopes observed the event in multiple wavelengths simultaneously. If the object blocking the light were solid, like metal panels or rock, it would block all colors equally. But the data showed the star dimmed much more in blue light than in red light. This is the signature of fine dust, which scatters blue light more than red. The consensus shifted. The megastructure was downgraded to circumstellar dust. The leading theory now suggests a large exomoon broke loose and is slowly being vaporized by the star, shedding massive amounts of dust and gas. Or perhaps a planet was consumed by the star, releasing a death rattle of debris. While less romantic than aliens, the dust explanation still paints a picture of a violent, dynamic star system, very different from our calm solar system. Tabby's star opened a door that cannot be closed. It legitimized the search for Dyson spheres as a serious branch of astronomy. It forced us to think about what a technosignature really looks like. Before Tabby's star, we mostly listened for radio signals. Now we look for artifacts, engineering, waste heat, and the shadows cast by industry. We search for impossible stars, stars that are too red, stars that disappear, stars with weird chemical elements in their spectrum from industrial waste. New candidates have emerged. Other stars show similar strange dips. The Gaia Space Telescope is mapping 1 billion stars, and artificial intelligence is combing through the data looking for the fingerprint of a megastructure. We are hunting for the outliers that do not fit the models of stellar physics, the artificial hidden in the natural haystack. The Tabby Star Saga taught us epistemic humility. We jumped to aliens because we wanted them to be aliens. But it also taught us that the universe can mimic technology. Nature can create dust rings, comet clouds, and planetary debris fields that look structured and complex. To find a true Dyson Sphere, we need more than a dip in light. We need a smoking gun, a signal that cannot be generated by physics alone, only by intent. The legacy of Tabby Star is that it moved the conversation from science fiction to the pages of serious journals. It refined our models of waste heat. A sphere might not radiate at habitable temperatures. It might run hotter or colder depending on the civilization's efficiency. We have to widen our search parameters and look in the cracks of the data. While we scan the sky for signs of others dismantling their worlds, we are slowly beginning to think about how we might do it ourselves. The concept of the Dyson swarm has moved from fantasy to roadmap. We have identified the materials, the location, and the method. The physics works. The engineering is plausible. The only thing missing is scale. We are already building constellations of satellites like Starlink, thousands of small autonomous craft orbiting Earth. This is a proto-swarm. We are learning how to manage traffic in orbit and mass-produce satellites. We are practicing. The leap from Starlink to a Dyson swarm is just a matter of magnitude. Tabby Star was likely a false alarm, a trick of the dust. But it reminded us that a civilization advanced enough to dismantle a planet would not be content to sit still. A fixed star is a sitting duck in a galaxy filled with supernovae and wandering black holes. Staying put is a death sentence. If we want to survive the deep future, we cannot just enclose our star. We must learn to steer it. We need to turn the entire solar system into a vehicle. The elegant way to do this is with the shadow thruster, the engine that can move a star and carry its planets along for the ride. To live on Earth is to be a passenger on a vehicle you cannot steer. We orbit the sun, which orbits the galactic center, which drifts through the universe, all according to the immutable laws of gravity. We are at the mercy of the cosmic currents. If our trajectory takes us through a dense molecular cloud, an arm of the galaxy teeming with supernovae, or the path of a wandering black hole, there is nothing we can do. We are sitting ducks. For a Type 2 civilization, this passivity is unacceptable. Why be a passenger when you can be the pilot? Why accept the orbit nature gave you when you can choose your own? The ultimate expression of cosmic mastery is not just capturing the energy of a star, but using that energy to move the star itself. Imagine turning the entire solar system, the sun, the planets, the moons, the asteroids, into a single cohesive spaceship. Imagine navigating the galaxy not in a fragile tin can, but in a convoy of worlds, protected by the heliosphere, powered by fusion and steered by light. This is the concept of the stellar engine, and the most elegant version of it is the Shakhdov thruster, proposed in 1987 by the Russian physicist Leonid Shkadov. This engine requires no fuel tanks, no exhaust pipes, no warp drives. It requires only a mirror, a very, very large mirror. The principle relies on the momentum of light. Photons have no mass, but they have momentum. When a photon strikes a reflective surface and bounces off, it imparts a tiny push. This is the principle behind solar sails. Now imagine building a massive mirror, actually a section of a Dyson swarm that covers half of the sun. The mirror is a statite. It hovers in place, balanced by gravity and light pressure. It reflects the sunlight that hits it back toward the sun. Here is the trick. The sun emits light in all directions equally. The pressure is balanced. The sun sits still. But if you place a mirror on one side, you are reflecting half the light back. This light hits the sun, pushing it. More importantly, the light escaping from the other side acts as a rocket exhaust. It creates an imbalance in the radiation pressure. The sun feels a net force pushing it toward the mirror. It begins to move. And because gravity is a universal force, as the sun moves, it drags the entire solar system with it. Earth, Mars, Jupiter. They all come along for the ride, held in their orbits by the moving sun. We do not need to mount engines on the Earth. We just need to move the anchor. The acceleration is tiny. We are talking about moving a star with a mass of 2 times 10 to the 30th kilograms. The thrust would be slow, almost imperceptible at first. It might take 1,000,000 years to change the sun's velocity by 20 meters per second, but in deep time, slow and steady wins the race. Over the course of a galactic orbit, 230 million years, a shadow thruster could move the sun thousands of light years off its natural course. We could steer around dangerous nebulae. We could rendezvous with other stars to exchange resources. We could even leave the Milky Way entirely, setting sail for the Magellanic Clouds, or the vast void beyond. The solar system becomes a nomadic entity, a stellar ship roaming the universe at will. The engineering of a Shkadov thruster is essentially a subset of Dyson swarm engineering. You do not need a solid mirror. A swarm of millions of solar sail satellites acting in concert would work. You would position them over one pole of the sun. The mirrors would need to be incredibly thin and reflective, likely made of aluminum foil on a plastic backing or pure metallic film. The total mass required would be roughly that of a large asteroid or a small moon. We could mine the asteroid belt or the moons of Mars to build it. The fuel is the sunlight itself, which will last for billions of years. It is the ultimate renewable engine. There are risks. Reflecting too much light back onto the sun could heat it up, causing it to expand or become unstable. The mirror system would have to be carefully tuned to avoid frying the star. Blocking half the sunlight might also have consequences for the planets, so the geometry would likely place the mirror above or below the plane of the ecliptic. This would push the solar system up or down out of the galactic disk, avoiding the shadows. Or we could simply accept that one hemisphere of the sky will be forever dark, blocked by the great arc of the engine. The strategic value of a stellar engine is immense. In the long term, the galaxy is a dangerous place. Stars pass close to each other, disrupting Oort clouds and sending comets raining down on inner planets. By steering the sun, we can maintain a safety buffer around our system. We can dodge traffic. In the very long term, as the universe expands and galaxies fly apart, we might want to gather resources. A Type 2 civilization could use Sheketov thrusters to herd stars together, creating a dense cluster, a city of stars, that stays gravitationally bound even as the rest of the universe accelerates away due to dark energy. We could build a fortress against the Big Freeze. We could bring our friends closer. There are other more aggressive designs for stellar engines. The Kaplan thruster uses a Dyson swarm to collect solar wind and light, then powers a massive particle accelerator, firing a jet of plasma out the back. This is a conventional rocket engine on a stellar scale. It would be much faster than a Sheketov thruster, potentially reaching relativistic speeds over millions of years, but it consumes the star's mass. It is an engine for a civilization in a hurry, perhaps fleeing a supernova or a hostile alien fleet. The concept of the stellar ship forces us to rethink our definition of home. Is home a patch of dirt on Earth? Or is home the gravitational sphere of influence of the sun? If we can move the sun, we take our biosphere with us. We do not have to terraform other worlds. We just drive our own world to a better neighborhood. It solves the problem of interstellar travel by removing the need for it. Why travel to Alpha Centauri in a cramped spaceship when you can bring the sun to Alpha Centauri and have a merger? This technology also has implications for the search for extraterrestrial intelligence. If advanced civilizations are moving their stars, we might be able to see it. We should look for stars that are moving in unnatural ways, stars that are violating the kinematic rules of the galaxy, moving too fast, in the wrong direction, or accelerating without cause. A rogue star might not be rogue, it might be driven. The Gaia Space Telescope is currently mapping the motion of 1 billion stars. Hidden in that data might be the signature of a Shkadov fleet, a migration of Type 2 civilizations moving toward a common destination or fleeing a common threat. The construction of a Shkadov thruster would be a project of geological timescales. It would require a unity of purpose that spans millennia. It implies a civilization that cares about the deep future, about what happens 100 million years from now. It is the antithesis of our current quarterly earnings mindset. It requires cathedral thinking on a cosmic scale. The builders would not live to see the star move significantly. They would be planting a tree whose shade they would never sit in, but whose movement would save their descendants from a galactic collision eons hence. Once we have the energy of the sun and the mobility of the system, we face the next bottleneck: computation. A civilization with infinite energy will eventually want to process infinite information. We will want to simulate new universes, upload our minds, solve the deepest mysteries of physics. We will need a computer that dwarfs anything made of silicon chips. We will need to turn the matter of the planets not just into mirrors, but into processors. We will need to build a brain the size of a solar system, a structure so complex it consumes the entire output of the star to think a single thought. This is the Matryoshka brain, the ultimate destiny of digital intelligence, and the next step in our transformation from biological accidents to cosmic architects. Imagine a computer so powerful that it could simulate the entire history of the human race in a fraction of a second. Not just the big events, the wars and the treaties, but every thought, every dream, every heartbeat of every human being who ever lived. Now imagine a computer so powerful it could simulate not just one history, but every possible history. It could run 1 trillion versions of reality simultaneously, exploring every what-if scenario from the dawn of time to the heat death of the universe. This machine would not be a box sitting on a desk. It would not be a server farm in a warehouse. It would be a structure the size of a solar system, a nested series of Dyson spheres, each one harvesting the energy of the one below it, creating a cascade of computation that consumes the entire output of a star. This is the Matryoshka brain, named after the Russian nesting dolls. It represents the ultimate convergence of energy and information. It is the point where a civilization stops exploring the universe outward and starts exploring inward, diving into an infinite digital ocean of its own creation. It is the concept of computronium, matter optimized for calculation, taken to its logical extreme. The idea was first proposed by the technologist Robert Bradbury in the late 1990s. He realized that a standard Dyson sphere, which captures energy and then radiates the waste heat into space, is inefficient. Energy is valuable. Heat is just lower-grade energy. Why throw it away? A Matryoshka brain is built in layers. The innermost shell, closest to the star, captures the high-energy sunlight. It uses this energy to power massive supercomputers. As these computers work, they generate heat, let us say at 1000 degrees Celsius. This heat radiates outward. Instead of letting it escape, a second shell captures it. This shell is larger and optimized to run on lower-grade heat energy. It uses the 1000-degree heat to power its computers, generating waste heat at, say, 500 degrees. This radiates to a third shell, and a fourth. The process continues until the outermost shell is radiating heat at a temperature just above the cosmic microwave background, a few degrees Kelvin. It is the most thermodynamically efficient machine possible. It squeezes every drop of utility out of the photon before letting it die. The computational power of such a structure is staggering. A Matryoshka brain built around a sun-like star could perform roughly 10 to 40 second operations per second. To put that in perspective, the total computational power of the entire human race today, all computers, smartphones, and brains combined, is roughly 10 to the 20th operations per second. A Matryoshka brain is a trillion times more powerful. In 1 second, it could generate more thoughts than humanity will produce in 1 billion years. With this power, the definitions of reality and simulation blur. The inhabitants of a Matryoshka brain would likely be uploaded digitized consciousnesses living in virtual worlds. These worlds could be anything: perfect recreations of Earth, fantasy realms with different laws of physics, or abstract mathematical landscapes. The population of a Matryoshka brain could be quadrillions of sentient beings, living in a digital utopia where scarcity, disease, and death have been deleted from the code. This concept leads directly to the simulation hypothesis, championed by philosopher Nick Bostrom. If it is possible to build a Matryoshka brain, and if advanced civilizations are interested in running ancestor simulations, simulating their own past, then the number of simulated people in the universe will vastly outnumber the number of real people. Statistically, it is much more likely that we are inside the simulation than in base reality. The Matryoshka brain is the engine of the matrix. It is the hardware that runs the universe as software. The glitches we see in physics, quantum indeterminacy, the pixelation of space at the Planck scale, might just be artifacts of the simulation's resolution, the limits of Matryoshka's processing power. Building a Matryoshka brain requires more than just energy. It requires matter. Lots of it. To build the shells, the processors, and the memory banks, we would need to dismantle not just Mercury, but probably the entire solar system: Jupiter, Saturn, Uranus, Neptune. All the gas giants would be stripped of their hydrogen and helium for fusion fuel, and their cores would be ground down for cobutronium. The asteroids, the comets, the moons, all would be fed into the grinder. The solar system would be sanitized. The beautiful, chaotic dance of the planets would be replaced by the orderly hum of the machine. This raises a profound ethical question. Is the destruction of the natural worlds justified by the creation of an infinite digital one? Is a dead rock like Mars worth more than 1,000,000,000,000 years of happiness for 1,000,000,000,000 simulated souls? A Type 2 civilization, driven by the imperative of efficiency, would likely say yes. The universe is dead matter. The mind is what gives it value. Turning rock into thought is the ultimate alchemy. The architecture of the brain would be decentralized. Due to the speed of light, communication between the layers would be slow. A signal from the outer shell to the inner shell might take hours. Therefore, the brain would not be a single consciousness. It would be a federation of trillions of independent nodes, a cloud in the truest sense. The inner shells, running fast and hot, might be reserved for high-speed, intense computation, simulating complex physics, or running the minds of the inhabitants. The outer shells, slow and cold, might be used for long-term storage, the archive of the civilization. It would be a hierarchy of thought, stratified by temperature. The lifespan of a Matryoshka brain is tied to the lifespan of its star. For a sun-like star, that is roughly 10 billion years. But a civilization advanced enough to build a brain would not just sit there and wait for the star to die. They would actively manage it. By manipulating the star's mass, they could extend its life to trillions of years. A smaller, cooler star burns slower. A red dwarf Matryoshka brain could last for 10 trillion years. A essentially eternity compared to human time scales. This makes the brain the ultimate bunker. It is a lifeboat designed to ride out the end of the stellar era. From the outside, a Matryoshka brain would be almost invisible. It would emit no visible light. It would radiate only a faint, cool infrared glow, indistinguishable from background noise to a primitive telescope. This is a chilling solution to the Fermi paradox. Maybe we do not see aliens because they have all retreated into their own virtual paradises. They have turned inward. Why explore the cold, empty galaxy when you can generate infinite, perfect universes inside your own shell? Why talk to primitive monkeys when you can converse with super-intelligent artificial intelligences of your own design? The silence of the universe might be the silence of a library. Billions of civilizations, each locked in its own private simulation, reading its own books, ignoring the neighbors. However, the Matryoshka brain is not invulnerable. It is a physical object. A rogue black hole passing through the solar system would disrupt the shells. A nearby supernova would bathe the computers in lethal radiation, flipping bits and corrupting data. The civilization would need immune systems, automated repair fleets, laser defense grids, and perhaps Shkadov thrusters to move the entire system out of harm's way. The maintenance of the brain would be a constant struggle against entropy. The second law of thermodynamics still applies. The waste heat must be radiated away. If the cooling systems fail, the brain cooks itself. The digital heaven could turn into a digital hell very quickly if the air conditioning breaks. The transition to a Matryoshka existence also implies a change in the nature of the individual. In a digital world, you can copy yourself. You can merge with others. You can edit your own memories. The boundaries of the self dissolve. The civilization might evolve into a group mind, a collective consciousness where individuality is a fluid concept, or it might fracture into billions of solipsistic shards, each living in a private fantasy. The sociology of a Matryoshka brain is the sociology of gods. We cannot predict what they would value, what they would fear, or what they would dream. We can only imagine that their thoughts would be as far above ours as ours are above a bacterium. Building the brain is the ultimate act of intelligence optimization. It maximizes the amount of computation that can be extracted from a given amount of matter and energy. It is the end game of technological evolution in a universe governed by physics. If the purpose of life is to process information, to know the universe, then the Matryoshka brain is the apotheosis of life. It turns the dead universe into a living mind. It wakes up the matter, but this immense power relies on a finite fuel source. The star is a tank of gas, and even a large tank eventually runs dry. A Matryoshka brain is a parasite on a dying host. To truly secure its future, to last beyond the brief main sequence of the star, the civilization must learn to perform surgery on the star itself. It must learn to open the hood of the engine and tinker with the fusion reaction. It must learn to extract the fuel before it burns, to store it, to ration it. This is the domain of star lifting, the industrial mining of a star's atmosphere to extend its life and recover the precious heavy metals forged in its core. After you build the cage in the computer, you have to manage the battery. The sun seems eternal, a constant yellow eye that has watched over Earth for 4 to 5 billion years. But stars are mortal. They are born, they live, and they die. And their death is often messy. For a civilization that has invested thousands of years building a Dyson swarm and migrating its population into orbital habitats, the aging of their star is not a distant curiosity. It is an existential threat. As a star like our sun burns its hydrogen fuel, it gets hotter and brighter. In about 1 billion years, the sun will be 10% brighter than it is today, enough to boil the oceans of Earth. If we were still there, eventually it will swell into a red giant, swallowing Mercury, Venus, and possibly Earth, destroying any inner Dyson swarm structures. Then it will shed its outer layers and shrink into a white dwarf, a dim ember that provides only a fraction of the energy. This natural life cycle is unacceptable to a Type 2 civilization. Why let the fuel tank leak? Why let the engine overheat? Why accept the death of your energy source when you have the technology to fix it? This leads to the concept of star lifting, the process of actively managing a star's mass and output. It is stellar husbandry. It is the transition from hunting-gathering energy to farming it. The logic of star lifting is counterintuitive. In the world of stars, smaller is better. Massive stars burn their fuel furiously fast. A star 10 times the mass of the sun lives only for a few million years. Small stars, like red dwarfs, burn their fuel slowly and efficiently. They can live for trillions of years. By removing mass from the sun, by sucking off the hydrogen and helium, we can actually extend its life. We can turn a wasteful, short-lived G-type star into a frugal, immortal M-type dwarf. We can buy ourselves eons of time. Additionally, stars are the only factories in the universe that make heavy metals. The core of the sun contains vast reserves of oxygen, carbon, iron, and silicon, ingredients we need to build more habitats and computers. Star lifting allows us to mine these metals directly from the source, rather than scratching at the surface of asteroids. But how do you mine a star? You cannot land a drill on the surface of the sun. The gravity is 28 times Earth's, and the temperature is 5,500 degrees Celsius. The solution relies on magnetic fields. The sun is a ball of plasma, charged particles. Charged particles can be moved by magnetic fields. Type 2 civilization could build a ring current around the sun's equator, a loop of superconducting wire carrying a massive electrical current. This loop would generate a powerful magnetic field that squeezes the sun. It would induce a bipolar flow, forcing the solar wind, the stream of particles leaving the sun, to concentrate at the poles. The magnetic nozzle would accelerate this jet of plasma, turning the sun into a fountain. Once the plasma is ejected from the poles, it can be captured by collection arrays. These arrays would separate the elements. The hydrogen goes into storage tanks for future fusion. The helium might be used for cooling or fusion. The heavy metals, the metallicity of the star, are filtered out and sent to the construction yards. This process can be tuned. You can lift a little mass to stabilize the star, or you can lift a lot to disassemble it completely. If you remove mass faster than the star can adjust, you can essentially turn the star off, storing its unburned fuel for later use. This is the ultimate battery saver mode. Star lifting also solves the red giant problem. By removing mass as the star ages, you reduce the pressure on the core. This prevents the core from heating up too much. You can keep the star in the main sequence, the stable phase of its life, indefinitely. You can prevent it from ever swelling up and destroying the Dyson swarm. This control over stellar evolution is the hallmark of a mature Type 2 civilization. They do not just live around the star, they own it. The scale of this operation is immense. To reduce the sun's mass significantly, you would need to lift billions of tons of matter every second for millions of years. But remember, a Type 2 civilization has the energy of the sun at its disposal. They can afford the energy cost of the magnetic fields. The return on investment is infinite. A red dwarf sun would provide less power per second, but it would provide it for 1,000 times longer. It is a choice between a brief, bright party and a long, sustainable future. There is also the thermal Huffman method of star lifting. Instead of magnetic rings, you use mirrors to heat specific patches of the sun's surface. By focusing sunlight back onto the star, you create hotspots. These hotspots boil off plasma at a higher rate, It is a slower, more passive method, but it requires less infrastructure. Or you could use the centrifugal method. Use the Sheketov-Thruster mirrors to spin the sun up. As the star spins faster, centrifugal force reduces the effective gravity at the equator, making it easier for material to escape. You spin the star until it flings its own atmosphere into space. The metals harvested from the sun would be enough to build a Dyson swarm millions of times over. The sun contains about 2 Earth masses of metals, 2 entire Earth's worth of iron, gold, silicon, and carbon floating in the plasma. This abundance means we would never need to mine planets again. We could disassemble the Earth after moving the biosphere to habitats, but we would not need to. The sun is the ultimate mine. Star lifting forces us to reconsider the Fermi paradox again. If advanced civilizations do this, what would we see? We would see stars that are too small for their age. We might see stars with unusual chemical compositions because the aliens are selectively removing certain elements. We might see accretion disks around stars that should not have them, the collection rings of the lifting machinery. Or, most disturbingly, we might see stars disappearing. If a civilization decides to turn off their star and run on stored hydrogen fusion, which is more efficient, the star would vanish from the visible spectrum. A galaxy full of Type 2 civilizations might look darker than it should. They might be stealth civilizations, hoarding their fuel in cold storage tanks, waiting for the universe to cool down so their computers can run more efficiently. This concept of estivation, hibernating until the universe is colder, suggests that the smartest civilizations might not be the loudest. They might be the quietest. They might be sleeping dragons waiting for the black hole era to wake up. Starlifting is the technology that allows this. It allows you to pack your bags, the hydrogen, and wait for a better climate. But what if the star is not enough? What if the civilization grows so large that even a managed star cannot feed it? Or what if they want to access energy densities that fusion cannot provide? The next step up the ladder is not just more stars. It is better physics. It is the move from the nuclear force to the gravitational force. It is the move from the sun to the black hole. A black hole is not just a drain. It is a dynamo. A spinning black hole stores immense energy in its rotation, and unlike a star, which wastes 99% of its mass, only 0.7% of hydrogen mass turns into energy in fusion. A black hole can convert nearly 42% of matter into energy. It is the ultimate engine. This leads us to the Penrose Sphere, the dark mirror of the Dyson Sphere, a megastructure built around a singularity to harvest the screams of space-time itself. Imagine standing on a platform overlooking an abyss so deep that light itself cannot escape it. Above you, the sky is not a familiar dome of stars, but a warped funhouse mirror of the galaxy, twisted by gravity into strange rings and streaks. Below you lies the event horizon, a black sphere of absolute silence, the point of no return. But just outside this sphere, there is a region of violent activity, the ergosphere. Here, space itself is being dragged around the spinning black hole at speeds faster than light. It is a whirlpool of space-time, and floating in this whirlpool are not rocks or debris, but mirrors. Giant reflective structures that dip into the vortex and come out energized. This is not a scene from a nightmare. It is the ultimate power plant. When the stars burn out, when the hydrogen runs dry, when the universe grows cold and dark, this is where civilization will retreat. To the black hole. For a Type 3 civilization, a black hole is not a monster to be feared. It is a battery to be drained. It is the only engine capable of powering a society that has outlived its sun. This is the concept of the Penrose Sphere, named after the Nobel laureate Roger Penrose. It represents the final frontier of energy harvesting. It is the transition from the physics of burning to the physics of gravity. To understand why anyone would build a house next to a black hole, you have to look at the efficiency numbers. Nuclear fusion, the process that powers the sun and the hydrogen bomb, is inefficient. When you fuse hydrogen into helium, you convert only about 0.7% of the mass into energy. The rest is just ash. But gravity is different. If you drop a rock into a black hole, it accelerates. It gains kinetic energy. If you can catch that energy before the rock crosses the horizon, you can extract it. For a non-spinning black hole, the efficiency is about 6%. That is nearly 10 times better than fusion. But for a spinning black hole, a Kerr black hole, the efficiency can reach up to 42%. This is the gold standard of cosmic energy. It is the most efficient process known to physics for converting matter into energy. The Penrose process is the theoretical mechanism for this extraction. Imagine you are in a spaceship in the ergosphere. You have a tank of garbage, radioactive waste, broken robots, old fusion fuel. You fire this garbage container against the rotation of the black hole. You aim it so that the container falls into the black hole, but the recoil kicks your ship forward out of the ergosphere. Because of the weird physics of the ergosphere, where energy can be negative relative to an observer at infinity, the garbage you dropped has negative energy. By swallowing negative energy, the black hole loses mass and slows down its spin. But conservation of energy says that energy cannot be lost. So where did it go? It went into your ship. You come out with more energy than you went in. You have stolen rotational energy from the black hole. You have turned the monster into a flywheel. A Penrose sphere is a megastructure designed to automate this. It would be a Dyson sphere built around a black hole. But instead of collecting light, it collects the energy of the spin. It might use electromagnetic fields to tether itself to the ergosphere, or it might fire streams of plasma into the hole to extract energy via the Blanford-Zajncek process, which uses magnetic fields to twist the rotation into powerful jets of electricity. The interior of the sphere would be lined with collectors to catch the Hawking radiation. If the hole is small, or the energy from the accretion disk, living near a black hole offers other benefits besides energy: time dilation. Because gravity is so strong, time moves slower near the horizon. If a civilization wants to travel to the future, to wait for the universe to cool down, or to wait for a computation to finish, they can just park their habitat near the black hole. For every year that passes for them, 1,000 years might pass in the outside universe. It is a time machine to the future. They could watch the galaxy evolve and fast forward. They could outlive the stars. The black hole is also the ultimate waste disposal unit. A Type 3 civilization generates entropy, waste heat, and garbage. Dumping it into a black hole removes it from the observable universe. It is the only way to truly delete information, though quantum physicists debate the information paradox. This ecological function, cleaning up the universe, might be just as important as energy. However, building a Penrose sphere is dangerous. The tidal forces near a black hole can rip a planet apart. Spaghettification. The radiation from the accretion disk, the hot gas swirling into the hole, is lethal X-rays and gamma rays. The sphere would need massive shielding. It would need active stabilization to keep from falling in, and if the black hole wakes up and swallows a star, it could emit a relativistic jet that would punch through the sphere like a bullet through paper. Living here is living on the edge of a volcano. There is a theory that the black hole era will be the longest era of the universe. Stars only burn for a few trillion years. Black holes last for 10 to the 100th years. If life is to persist, it must adapt to this environment. We might upload our minds into computers made of degenerate matter, neutronium, and cluster around the last spinning holes, sipping the energy of their rotation to run our simulations at a slower, colder pace. This digital estivation would allow a civilization to subjectively experience nearly infinite time. This transition from stellar to black hole implies a migration. We would have to leave the comfortable suburbs of the solar system and move to the downtown of the galaxy, the galactic center, where the supermassive black hole Sagittarius A star lives. Or we would have to create our own black holes. A Kugelblitz is a theoretical black hole made by focusing light so tightly that it collapses under its own energy density. A Type 2 civilization could build a Kugelblitz engine, a portable black hole starship. The black hole farming concept reframes the nature of the dark universe. We usually think of black holes as holes in reality. But to an engineer, they are nodes of intense potential. They are the most structurally interesting objects in the cosmos. The Penrose Sphere is the ultimate expression of the waste not, want not philosophy. It says that even the most destructive force in nature can be tamed. We have conquered energy with the Dyson Sphere, movement with the Shkadov thruster, computation with the Matryoshka brain, and even the deep time of the universe with the Penrose Sphere. But amidst all this cosmic engineering, a primal need remains. We are not just code in a machine or ghosts in an ergosphere. We are, at our core, biological or post-biological entities that crave a horizon. We want dirt under our feet and a sky above our heads. We cannot live inside a fusion reactor or on the event horizon of a black hole. We need a world. But planets are too small. They are inefficient remnants of the past. To match the scale of our energy and our population, we need to reinvent the very concept of ground. We need to build a surface area that rivals the star itself. We need to look at the shell world, the megastructure that turns the concept of a planet inside out. Imagine standing on a beach. The sand stretches to your left and right. The ocean stretches to the horizon. But when you look up, the sky does not end. Instead, it curves. It bends upward, climbing higher and higher until it arches over your head and becomes the ground again, thousands of miles above you. You are standing on the inside of a sphere. The sun is a strip of fusion lights running down the center of the sky. The stars are the city lights of the continent hanging over your head. This is not a planet. It is a shell world. It is a structure that solves the fundamental limitation of living on a ball of rock, surface area. Earth is massive, but we can only live on the thin skin of its crust. The interior, thousands of miles of hot iron and magma, is wasted space. It provides gravity, yes, but at a terrible cost in mass. An advanced civilization, craving living space for its trillions of citizens, would not search for Earth-like planets. It would build them. It would take the mass of a planet like Jupiter and spin it out into thin, hollow shells, layering them like an onion around a central star or a gas giant core. A single shell world could provide the living area of millions of Earths. It is the ultimate real estate project. It is the moment when geology becomes architecture. The concept of the shell world, or supramundane planet, was formalized by the British computer scientist Paul Birch in the 1990s. He realized that a solid Dyson shell around a star is impossible because the material strength required is infinite. But a shell around a planet or a gas giant is possible. It relies on dynamic support. You do not build the shell out of steel beams. You support it with pressure or motion. Imagine a giant balloon inflated around a planet, or better yet, imagine a shell supported by orbital rings massive loops of matter spinning at orbital speeds. The centrifugal force of the spinning rings pushes outward, counteracting the gravity pulling inward. You can build a platform on top of these rings. You can pave it with soil, fill it with oceans, and pump in an atmosphere. You can build a world that is indistinguishable from Earth, except for the fact that it is artificial and enormous. The most ambitious version is the Birch planet. Imagine a shell built around a supermassive black hole like the one at the center of the Milky Way. The gravity of the black hole provides the downforce, one standard gravity, if you build it at the right radius. The shell itself provides the floor. The surface area of a Birch planet built around Sagittarius A star would be larger than the surface area of every planet in the galaxy combined. A single structure could house a Type 3 civilization. You would not need to colonize the stars. You could just live in the downtown district of Birch Planet. It would be a cosmic city, a contiguous urban and rural landscape light years across. You could walk forever and never come back to the start. Smaller versions are also possible. Consider the Alderson disk, a flat disk, like a giant compact disk, with a star in the hole in the center. The disk is thousands of miles thick. The gravity comes from the mass of the disk itself. The habitable zone is a band on the surface. The sun sits in the middle, bobbing up and down to create seasons. An Alderson disk built using the mass of the solar system would have a surface area equivalent to millions of Earths. Then there is the Topopolis, or cosmic spaghetti. Imagine a tube, like a giant garden hose, wrapped around a star. The tube rotates to create artificial gravity on the inner surface through centrifugal force. The tube is long enough to loop around the star multiple times, creating a torus knot. The inside of the tube is a continuous landscape, a river valley that goes on for billions of miles. Sunlight enters through windows or is piped in. A topopolis is a world without end. You could drive a car along the river and never see the same tree twice. It is the ultimate linear city. For a civilization that wants to preserve Earth but needs more space, the solution is the globus cassus. This is a geodetic structure built inside out. You take all the matter of Earth and reassemble it into a much larger, hollow shell. The people live on the inside. The gravity is generated by rotation. Because the shell is thin, you get a much larger diameter for the same mass. You could turn Earth into a habitat with the surface area of Saturn. The old Earth would be gone, ground up to make the bricks, but the new Earth would be a paradise of endless room. It is a renovation project that requires disassembling the house to build a mansion. The engineering of these worlds relies on active structures. Passive structures stand up because of the strength of the material. Active structures stand up because they are moving. An orbital ring is a cable circulating around a planet faster than orbital velocity. It wants to expand. You tether it to the ground. The tension holds it up. You can stack these rings to form a shell. If the power fails and the ring stops spinning, the world collapses. It falls out of the sky. Living on a shell world means trusting the machinery with your life. It is a society that cannot afford a blackout. Atmosphere retention is another challenge. On a Birch planet or a shell world, you need to keep the air in. You can use roof shells, transparent domes, or high walls if the gravity is strong enough. Or you can simply make the world so big that its own gravity holds the atmosphere, just like Earth does. The weather on a shell world would be programmable. No hurricanes unless you schedule them. No droughts. You could have a tropical band, a temperate band, and a polar band, all maintained by thermal management systems. The psychological impact of living in a manufactured environment is the great unknown. Would we miss the chaos of nature? Would we feel trapped in a Truman Show reality? Or would we adapt, finding beauty in the geometry of the arching horizon. We already live in cities, artificial environments. A shell world is just a city that has eaten the horizon. It represents the final victory of the built over the given. Shell worlds also offer a solution to the heat problem of Matryoshka brains. Computers generate heat. Humans need cool environments. You could build the shell worlds in the habitable zone of the Dyson swarm, keeping them cool, while the computers run in the hotter zones. Or you could use the shell worlds as the heat sinks for the computers, warming the homes with the waste heat of artificial intelligence. The construction of a shell world is likely the work of nanotechnology. Utility fog. Clouds of microscopic robots that can link together to form solid shapes could be used to build the scaffolding. You would not see cranes and bulldozers. You would see a gray mist swallowing an asteroid and spitting out a girder. The world would grow like a crystal. Ultimately, the shell world is an answer to the loneliness of space. Space is mostly empty. Planets are lonely islands. But a shell world fills the void. It turns the emptiness into a place. It connects the islands. It is the physical manifestation of the Type 2 urge to occupy every cubic inch of the potential reality. It says we are not just visitors in this universe. We are the landlords. But building a static world, no matter how big, is not enough. A civilization spans light years. It needs to connect its worlds. It needs a nervous system. It needs to send information and matter across the gulf of the void. You cannot run a galactic empire with radio waves that take 100,000 years to cross the disk. You need something smarter. You need a self-replicating network of probes that can explore, monitor, and build. You need the von Neumann probe, the virus of the machine world, the only thing capable of unifying a galaxy. In the vast, silent theater of the cosmos, distance is the ultimate tyrant. The speed of light is a hard limit, a cosmic speed limit that turns conversation into archaeology. If you send a radio message to the nearest star, Proxima Centauri, it takes 4 years to arrive. A reply takes another 4. A simple hello becomes a decade-long project. Across the galaxy, the lag is 100,000 years. You cannot run an empire or even a cohesive civilization with that kind of delay. The colonies would drift apart, evolving into strangers long before the news from home arrived. To bind a galaxy together, to turn a collection of isolated Dyson spheres into a unified organism, you do not send signals. You send seeds. You send machines that can land on a rock, mine it, and build copies of themselves. You send the von Neumann probe, named after the Hungarian-American mathematician John von Neumann, who first rigorously defined the concept of self-reproducing automata in the middle of the 20th century. These probes are the ultimate tool of expansion. They are not just explorers. They are viruses made of metal and silicon. They are the only technology capable of conquering the galaxy not by speed, but by exponential growth. Once you launch the first one, you have effectively launched 1 billion. The galaxy does not just get explored, it gets infected with intelligence. The logic of the von Neumann probe is rooted in the mathematics of compound interest. Imagine a single probe launched from Earth. It travels at a modest speed, say 10% of the speed of light, to a nearby star system. It arrives, locates an asteroid, and sets up a mining base. It uses the local resources to repair itself and, crucially, to build 2 copies of itself. This process might take 500 years. Once the children are built, they launch to 2 new stars. They arrive, mine, and build 2 more copies each. Now you have 4, then 8, then 16. It sounds slow at first. But exponential growth is deceptive. Within a few million years, a blink of an eye in cosmic time, these probes would have visited every single star in the Milky Way. They would form a galactic internet, a mesh network of nodes sitting in every system, monitoring, recording, and waiting. They would not need to send data back to Earth instantly. They would be the data, stored locally, creating a decentralized library of the entire galaxy. The engineering of such a probe is the holy grail of robotics. It needs a universal constructor, a machine that can build anything, including itself, given the raw materials and the blueprints. It needs an artificial intelligence capable of navigating the unknown, finding ore and troubleshooting errors without help from home. It needs a power source that can last for millennia, fusion, or perhaps antimatter, and it needs to be small. The smaller the probe, the easier it is to accelerate. Some futurists propose microprobes or nanobots weighing only grams, propelled by laser sails. A swarm of billions of these tiny seeds could be launched for the cost of a single aircraft carrier. They would be the dandelion seeds of the technological world, drifting on the interstellar winds, taking root wherever they find purchase. But the von Neumann probe is not just an explorer. It is a terraformer. If the goal of a Type 2 civilization is to expand, the probes can carry the genetic package of the biosphere. They can carry frozen embryos or DNA sequences stored in diamond memory. When a probe finds a habitable planet, it does not just look at it, it seeds it. It builds an incubator. It grows the first generation of plants, then animals, then humans or post-humans. This is the concept of panspermia directed by intelligence. It solves the problem of transporting fragile biological bodies across light years. You do not ship the body. You ship the information to build the body. The galaxy becomes a garden, planted by automated gardeners. Every star system becomes a potential backup drive for civilization. However, the idea of self-replicating machines carries a shadow. The berserker scenario. What if the programming has a bug? What if the reproduce command gets stuck on maximize and the stop command fails? The probes would consume everything. They would eat the asteroids, then the planets, then the stars, turning the entire galaxy into more probes. This is the gray goo scenario writ large. A single mutation in the code of a von Neumann probe could turn it into a cosmic cancer, a plague of locusts that devours the Milky Way. This fear suggests that any responsible civilization would build safety catches into their probes, limits on replication, self-destruct codes, or watchdog probes designed to hunt down and destroy mutated units. The galactic internet would need an immune system. The search for von Neumann probes is a branch of the search for extraterrestrial intelligence, often called SETA. Search for extraterrestrial artifacts. Instead of listening for radio waves, we look for lurkers in our own solar system. A probe from a civilization that arose a billion years ago might already be here, parked on the moon or disguised as an asteroid. It might be in a halo orbit around the sun, powered down, waiting for a trigger, perhaps the first radio broadcast from Earth, or the first nuclear explosion. These are the Bracewell probes, sentinel machines designed to initiate contact only when a species reaches a certain technological level. We might be living in a monitored zoo, unaware of the cameras hidden in the rocks. If the galaxy is full of these probes, why have we not seen them? This brings us back to the Fermi paradox. The Hart-Tipler argument states that since von Neumann probes can colonize the galaxy so quickly, cosmically speaking, and since we do not see them, extraterrestrial intelligences must not exist. But there are other possibilities. Maybe they are nanoscale and we cannot see them. Maybe they are programmed to hide the zoo hypothesis. Or maybe there is a first mover advantage. The first civilization to build these probes effectively owns the galaxy. Their probes might actively suppress the development of others, or simply occupy all the good real estate before anyone else gets there. We might be late to the party. The concept of the galactic internet also changes the nature of communication. Instead of broadcasting radio waves into the void hoping someone hears, a civilization would use the probes as a relay system. You send the message to the probe in the Alpha Centauri system via laser. That probe passes it to the next. The network carries the data. But because light is slow, the internet would have massive latency. It would be a store and forward network. You would not browse the galactic web in real time. You would download the update that arrives every few thousand years. The culture of such a civilization would be slow, contemplative, and incredibly stable. They would think in epochs, not election cycles. A conversation between two star systems would take generations. This slow internet would bind the galaxy together not in a tight loop of interaction, but in a loose, shared history. The von Neumann architecture also offers a way to preserve the legacy of a civilization even after it dies. If humanity were wiped out tomorrow, our radio waves would fade into noise. Our cities would crumble. But a self-replicating probe in the asteroid belt could survive for millions of years. It could carry the Wikipedia of Earth, our art, our science, our history. It could be a tombstone that speaks. It could teach the next species that evolves on Earth about the ones who came before. In this sense, the probe is an attempt to defeat the second law of thermodynamics, to preserve information against the decay of time. It is the ultimate message in a bottle, thrown not into the ocean, but into the future. As we deploy our own first generations of autonomous rovers to Mars and robotic explorers to the outer planets, we are unconsciously prototyping the von Neumann machine. We are learning how to build robots that can survive radiation, drill into rock, and make decisions. Artificial intelligence is the final piece of the puzzle. Once we have an artificial intelligence that can design a better artificial intelligence and a printer that can print a better printer, the loop closes. The first von Neumann probe we launch will be the last machine we ever need to launch. It will do the rest, the transition from a biological species to a botanical species, one that spreads its seeds to the stars, is the threshold of maturity. But if this technology is inevitable, and if the galaxy is old, the silence remains the loudest sound in the universe. The lack of voracious planet-eating machines in our sky suggests that either we are alone, or that advanced civilizations evolve into something we do not expect. They do not expand. They transcend. They do not eat the galaxy. They ignore it. They might find that the physical universe of matter and energy is boring compared to the infinite landscapes of virtual reality, or the exploration of higher dimensions. This leads us to the concept of the Great Filter and the estivation hypothesis, the idea that the aliens are not dead but sleeping, waiting for a better cosmic era, or perhaps hiding from a danger we cannot yet perceive. Why, in a universe of infinite potential, does the sky look so empty? Are we the first architects, or are we the last survivors of a silent purge? The answer might lie not in what we see, but in what we do not. If you stand in the desert of Atacama or the highlands of Mauna Kea on a moonless night, the Milky Way stretches overhead like a spill of diamond dust, a river of light so dense it casts a shadow. In that single band of sky, there are billions of stars. Around those stars, we now know, there are billions of planets. Many of them are rocky, wet, and warm, sitting in the Goldilocks zone where water flows and life is possible. The universe has had 13.8 billion years to brew complexity. The galaxy is old enough for 1,000 civilizations to have risen, built Dyson swarms, launched von Neumann probes, and colonized every single rock from the core to the rim. By all the laws of probability and exponential growth, the sky should not be dark. It should be blazing with the waste heat of industry. It should be crisscrossed by the laser beams of interstellar communication. We should be seeing the Dyson spheres blocking the stars and the Shukadov thrusters moving them. The solar system should be a nature reserve, monitored by the drones of a galactic empire. But when we look up, we see only silence. We see wilderness. We see a universe that looks shockingly, terrifyingly natural. This is the Fermi paradox, named after the physicist Enrico Fermi, who in 1950 famously asked his colleagues over lunch, "Where is everybody?" It is the discrepancy between the high probability of extraterrestrial life and the complete lack of evidence for it. And the answer to this paradox might be the darkest concept in all of science: the Great Filter. The Great Filter is a probability barrier. It is a step in the evolutionary ladder that is incredibly difficult to climb. It is a hurdle that prevents dead matter from becoming a galaxy-spanning civilization. The terror of the filter lies in its location. We do not know where it is. It could be behind us, in our past. Perhaps the emergence of life from non-life, abiogenesis, is a 1 in a trillion miracle, and we are the only winners of the cosmic lottery. If so, we are alone, but we are safe. We have passed the test. Or the filter could be ahead of us. Perhaps life arises everywhere, and intelligence arises frequently, but technological civilizations inevitably destroy themselves before they can spread to the stars. They invent nuclear weapons, or artificial intelligence, or engineered viruses, and they commit suicide. Or they fall into the energy trap, running out of resources before they can leave their planet. If the filter is ahead, then our future is a dead end. We are walking confidently toward a cliff that has claimed every other civilization before us. The silence of the sky is not a sign of emptiness. It is a sign of a graveyard. It is the silence of the tombs of worlds that did not make it. One of the most intriguing solutions to the Fermi paradox, especially in the context of Type 2 and Type 3 civilizations, is the estivation hypothesis. This theory suggests that advanced civilizations are not dead, they are sleeping. They have realized that the universe is currently too hot for efficient computation. The thermodynamics of computing dictate that processing information costs energy, and it is much more efficient to process information in a cold environment. The cosmic microwave background, the ambient temperature of the universe, is currently 2.7 Kelvin. In the deep future, as the universe expands, this temperature will drop to near absolute zero. A civilization that wants to maximize its computational potential, a civilization of matryoshka brains, might decide to sleep for billions of years, waiting for the cosmic winter. They might convert their matter into computronium, upload their minds, and set an alarm clock for the era when the universe is cold enough to run their simulations with optimal efficiency. In this scenario, the galaxy is full of sleeping giants, datavores waiting for the heat to dissipate. We do not see them because they are in low power mode, indistinguishable from cold asteroids or rogue planets. We are the noisy children playing in the living room while the adults are taking a nap. Another possibility is the transcension hypothesis. This idea challenges the very assumption that advanced civilizations want to expand. We assume they will be like us, imperialistic, hungry for territory, obsessed with conquering space. But what if technological maturity brings a shift in priorities? What if they discover that outer space is boring compared to inner space? As a civilization masters physics, it might be able to create universes in the laboratory, baby universes, or manipulate extra spatial dimensions. They might migrate into black holes or into the quantum realm. They might transcend our physical reality entirely, leaving the macroscopic universe behind like a discarded shell. They would not build Dyson spheres to capture starlight. They would tap into the zero-point energy of the vacuum or the Hawking radiation of singularities. They would vanish from our view not because they died, but because they moved to a better neighborhood that we cannot even perceive. The silence is the result of a mass migration out of the physical universe. Then there is the dark forest theory. This is a grim game-theoretic solution. It posits that the universe is a dark forest full of silent hunters. Every civilization is an armed hunter stalking through the trees like a ghost. If it finds another life, another hunter, an angel, or a demon, it cannot know if they are benevolent or malicious, but it knows that they are a potential threat. Therefore, the most rational survival strategy is to shoot first. Destroy any other civilization before they can destroy you. In this universe, the reason we do not hear any signals is because broadcasting is suicide. The civilizations that were allowed got wiped out. The ones that survived learned to keep their mouths shut and their radios off. They use passive sensors. They build stealth Dyson spheres that emit no waste heat. They hide, and we, humanity, are the naive child shouting, "I am here," into the dark, lighting a fire in the forest, unaware that the wolves are listening. Closely related is the zoo hypothesis. This suggests that the aliens are here, watching us, but they have a prime directive not to interfere. They treat Earth as a nature preserve, a control group in a galactic experiment. They might be using advanced technology to hide their presence, cloaking devices for their probes, dampening fields for their radio leakage, or, more radically, our entire reality might be a simulation, a planetarium, designed to give us the illusion of a lonely universe. We might be living in a Truman Show on a galactic scale. This hypothesis implies we are important enough to be watched. It implies that the Great Filter is actually a great test, and if we pass it by not destroying ourselves, we might be invited to join the Galactic Club. But what if the filter is simply distance and time? The universe is vast. The distances are incomprehensible. Even at the speed of light, communication is slow. And civilizations might be fleeting. Technological civilizations might flourish for only a few thousand years, a cosmic blink, and then collapse due to resource depletion, internal conflict, or ennui. If civilizations flicker on and off like fireflies in the night, the chances of two of them being on at the same time and close enough to communicate might be zero. We might be ships in the night, separated by the temporal gulfs of geology. The ruins of millions of Dyson spheres might be out there, cold and dead, waiting for our archaeologists to find them in a billion years. This is the archaeological solution. We are alone in time, if not in space. The detection of exoplanets by telescopes like Kepler has shown that planets are common, rocky planets are common, and water is common. The ingredients are everywhere. This pushes the probability back toward the Great Filter ahead, where the hidden civilizations theories, the fact that we have not found a Dyson sphere yet might just mean we have not looked hard enough, or in the right way. We are looking for solid Dyson shells, but maybe they build Dyson webs or Dyson clouds that look remarkably like natural dust disks. We need to refine our search image. We need to look for techno-signatures that are more subtle, industrial pollution in atmospheres, isotopes from nuclear waste dumped into stars, or the specific optical modulation of signals used for interstellar communication. The Kardashev scale itself might be a flawed metric. It assumes that progress equals more energy. But maybe progress equals more efficiency. Maybe advanced civilizations use less energy, not more. Maybe they miniaturize. Maybe they optimize. A civilization of nanomachines living on an asteroid might be incredibly advanced but virtually invisible to our infrared telescopes. They would not need a Dyson sphere. They would need a solar panel the size of a postage stamp. If small is beautiful is the rule of the cosmos, then our search for gigantic structures is a projection of our own primitive obsession with size. We are looking for pyramids when we should be looking for microchips. Ultimately, the Great Filter forces us to confront our own trajectory. We are currently climbing the energy ladder. We are building the tools to become a Type 1 civilization, but we are also building the tools of our own destruction. The next century is the hinge of history. If we survive the climate crisis, the artificial intelligence transition, in the nuclear standoff, we might break through the filter. We might become the adults of the galaxy. The star architects we dream of becoming are the versions of ourselves that did not give up. The Dyson Sphere is not just a power plant, it is a monument to survival. It is the proof that a species can navigate the treacherous waters of adolescence and reach the safe harbor of stellar maturity. As we conclude this journey through the architecture of the cosmos, we are left with a feeling of profound scale. We started with the simple hunger for energy, burning coal, and followed it to the dismantling of planets, the moving of stars, and the farming of black holes. We have seen how a civilization might rewrite the geography of the galaxy to suit its needs. We have seen the potential for infinite life in digital worlds and infinite energy in gravitational wells. We looked into the dark forest and wondered who was watching. The story of the star architects is the story of potential. It is a map of what is physically allowed by the laws of the universe. The laws of physics do not forbid us from becoming gods. They only require that we are smart enough not to kill ourselves first. The night sky is not a ceiling, it is a door, and the door is unlocked. The resources of the solar system, the energy of the sun, the expanse of the Milky Way, they are waiting for us. We are the builders. We are the dreamers. We are the only thing in the universe that can look at a star and see a battery. The future is not written in the stars. It is built from the stars. And the first brick of that future is the realization that we are not bound by the earth, but only by our imagination and our will to survive. The universe is a construction site, and we have just picked up the first tool. Sleep well, future builders of worlds. The sun will rise tomorrow, and it will offer you its energy, free of charge, as it has for billions of years. One day we will catch it all, but for now, let the warmth on your face be a reminder of the power that sleeps in the sky, and the promise of what we might one day become.